Welcome to the extra live session of molecular spectroscopy, a physical chemist perspective. I am Akuprabha Chaudhary, PMRF at the Department of Chemistry, IIT Bombay. I am taking this discussion session for the past 11 weeks, and today is a extra session, and the day after tomorrow on the Tuesday we will have the final live session, 12th week 12 live session. So today what I am planning to do is to discuss a few topics on means the few of the starting topics on the nuclear magnetic resonance NMR spectroscopy, and to solve some numerical problems from the Atkins. It will be very easy to start with, and let's see how much we can do. Today we are not going to solve the week 11 assignment problem. That week 11 and week 12 will be solved on the day after tomorrow. So to start with, on the electromagnetic spectrum, for now we have discussed, if you think of ultraviolet and this visible range, so we have discussed this portion in the electronic spectroscopy. Let me use my laser pointer. So we have used till now this in electronic spectroscopy, infrared in the vibrational spectroscopy, and microwave for the rotational spectroscopy. As you can see, from electronic to microwave, the energy decreases and the wavelength increases. Still, it's left with radio waves. Radio waves has a very high wavelength, right? But the energies are very less, as you can see, very low frequency like that. So that is actually comparable to the energy between the nuclear spins, and that's why it is used in NMR, nuclear magnetic resonance spectroscopy. So now let me get back to my pen and let us start the discussion. So firstly, nuclear magnetic resonance will takes place when there is an external magnetic field. So this external magnet, before this application of this magnetic field, all the nuclear magnet, if no, first with let me tell you that the essential criterion would be, so I will write NMR spectroscopy. So the essential criterion is that nuclear spin I should not be equals to 0. So it is similar to that, if you remember, for rotational spectroscopy or microwave spectroscopy, the dipole moment should not be 0, right? So there are some these essential criterions are there where the nuclear spin cannot be 0. So if it is not 0, and if it will have some whole integer or half integer number, then in presence of magnetic field they will split, and if they will split, then the energy gap between that, you can shine some light for that excitation to takes place, and if the resonance takes place, then that is your, you will get some spectra, and that is your NMR spectroscopy, right? So for that, let us see that upon what means upon what this nuclear spin may depend upon. So it is characterized that if your atomic mass is even atomic mass, and if your atomic number is also even, then your I, or nuclear spin, is going to be a 0. Some example of this is like your 12C or 16 oxygen. Okay, this is one of such. Now what will happen if your atomic mass is even but your atomic number is odd? What are the examples? Like if you remember 14N, so there your atomic mass is 14, which is a even number, but atomic number is 7, so odd. Even for a deuterium 2H, or suppose a boron 10B, right? In this case, you are going to get a whole integer as your I. What will happen in case of odd atomic mass? If you remember, so most commonly used NMR is obviously the proton NMR 1H and 13C, right? Or fairly real 15N 31P phosphorus. So in these cases, you are going to get an half integer as your I value. But the fairly common usage has been done with proton NMR and 13C. Okay. Now, if you want to correlate this thing with your rotational spectroscopy, if you remember that in your rotational spectroscopy J, that was the orbital angular momentum. In this case, you have to work with the nucleus spin angular momentum. So for that, the nucleus spin angular momentum is given by I into I plus 1 square root of that h cut. So in case of the rotational spectroscopy, in case of your rotational levels, it was j into j plus 1 square root of that multiplied by h. And what is the z component of that? Is mi into h, where mi is your different spin and mi can be plus half and minus half, for particularly for hydrogen or proton NMR if we discuss, or even 13C, because we, so let me check, stay in the call. Okay. And where does this mi value depends on? It depends on, it will be I minus 1, I minus 2, like it will go on till minus I. So there could be 2i plus 1 number of mi, right? It's fairly similar to, if you remember that rotational spectroscopy j plus 2j plus 1, what are the degeneracy like that. Okay. Now, what could be the angle between this angular momentum? Suppose mi is equal to half, that has an angular momentum, to the length would be root 3 by 2 h cut. What is for the mi is equal to minus half, that would be minus root 3 by 2 h cut, right? So what could be the angle between the each of these angular momentum with the z axis? So if I think like that, suppose these are the two spins. Okay. Now, for now, let me write it z. Okay. Suppose this is your minus half. Sorry, plus half. This is minus half. And it could be denoted as alpha spin, beta spin. For now, we are denoting it like that. Okay, alpha, beta. Okay. Now, for this case, what is the length? Length is root 3 by 2, right? In this case, what is the value? So, I is half, right? So, this case it is also root 3 by 2. But you can distinguish it by the z component, which would be, if I can draw it for you, it's not up to the scale, but think it like that way, that this is going to be half h cut and this is minus h cut by 2. So you can distinguish between, so they have different angles and due to that it has a different value. Different angles means angle with respect to z. But what is the angle from here z to this theta? If you think like that, then you will see that your cos theta is going to be root 3 by 2 is going to be on your denominator and half on your numerator, right? So it is something like 1 by root 3 and your theta in degrees will be 54.7 degree. Okay, for this particular case for proton NMR or 13C. Okay, so then what we can discuss, that how the splitting will be done. So splitting will be there. So once there is no magnetic field, then they are degenerate. There is no external magnetic field, then the spin states are degenerate. At once, for a steady magnetic field B0, there will be interaction between spin and this magnetic field, and that interaction energy can be written in terms of energy equals to minus this magnetic moment, mu is your magnetic moment, multiplied by this magnetic field, or mu is magnetic moment. Okay, it can be also written as gamma I, where your gamma is gyromagnetic ratio and I is obviously your nuclear spin or spin number. Now this gamma can be gyromagnetic ratio, so there is another term known as Gn. So that is your G factor for each nuclei. So how we can, so for mathematics, so various mathematical numerical problems you may require to know that particular formula also. So I am writing it here. So that is related to as gamma H cross can be written as Gi into mu n, where your Gi is a G factor for nuclei. So for separate nuclei it would be separate, means for a proton NMR, a proton nuclei it is different, for a carbon it is different. Another thing mu n, that is your actually nuclear magnetron. So that is a constant, and that is actually given by E h cut by 2 mp, mass of a proton. Okay, and E is the charge obviously, and as it is a constant it will be same for all the nuclei, which is something like 0.051 into 10 to the power minus 27, and unit is joule Tesla inverse. Okay, and the G factor varies from -6. It has a range -6 to +6. Now, if we consider only the magnetic field along the z-axis, because we have an idea, we don't want to work with all the components of I nucleus. No, if we want to only focus on the z component of I, then we need to look at the field along the z-axis only. So then the energy is along minus mu z b along c, where your mu z is gamma I. So that case, magnetic moment along the z-axis will only interact with your B0. Sorry, it will be and you can expand these also if you want. Gamma Iz you already know, that is MIH cross, and then you can write for a particular spin state it will be minus gamma MI H cross B0. Even you can write it in terms of the G factor, that is minus GI mu n MI B0. Okay. So that is your energy for a different spin states. So if you Mi is plus half, then what is going to be the energy? E for, suppose for alpha, E for, so here we are discussing on the 1H, or even if you think, means for a half integer like 13C, you can also think like that, but the energy of that alpha spin would be minus gamma H cut B0, right? Now what will be the energy for the beta spin? The plus half, A minus half will be gamma H cut B0. So in absence of magnetic field, it is like alpha and beta are like this. Of magnetic field. External lead. When the magnetic field is introduced, then the energy of your, this is your for the beta negative, that is going to destabilize, and this is going to stabilize for alpha, and the energy are like for here it is gamma H cross B0 for, sorry, plus, and here it is gamma H cross B0, and the energy gap delta E is given by, obviously I have made a mistake, it should be, it is plus half, right? Mi is minus half, Mi is plus half, and Mi is plus half for beta, minus half for this and plus half for this, so the gap would be actually gamma H across B0, which you can also write in terms of the Bohr magneton and the nuclear magneton, and in terms of the G factor multiplied by your magnetic field. Now we have one. So now when you shine this system with some light, and if this pin can flip, that means if you have a transition from alpha to beta, and if you are providing such energy, this delta E amount of energy, then so delta you can write obviously as H nu, right? In the case of resonance, your H nu would be equals to this gamma H cut B0, right? And this specific frequency of light is called as actually nu L, that is your Larmor precessional frequency. Okay. So when you equate this thing, your nu L comes out to be something like gamma B0 by 2 pi, right? And this is actually, this nu L is comes to be in the form of radio frequency, like certain hundreds of megahertz. So in NMR machines, you have all, means you generally hear the terms like this is a 300 megahertz NMR, or this is a 500 megahertz or a 400 megahertz NMR. What does that mean? So that actually refers to this radio frequency domain. For a bare nuclei, this is the particular radio frequency, and the magnet used there for creating the external magnetic field have that particular with respect to that frequency. Suppose Professor Datta has given you an example that when B0 was 12 Tesla, then your nu L was 500 megahertz, right? So like that, if your machine is 300 megahertz, then your B0, or the power of the magnet or the external magnetic field created by that magnet, is lesser than 12T. It is uh, it is proportional to your B0 is proportional to the Larmor frequency. That's so, but we are not going to discuss about the bare nuclei, right? Because in a molecule you are going to find out atoms or various kind of nuclei which are actually surrounded by different electronic environment. So going from a bare nuclei to a molecule where the nuclei is surrounded by a electronic environment. Now obviously your different nuclei will have different electronic environment, and based upon that their uh, Larmor frequency is going to be different for different nuclei, right? But how do we actually know what is going to be the means what is the effect of this electronic environment upon this nuclei? So if we look at that, then actually what is happening, that this electronic environment is going to create a shield along these nuclei, bare nuclei. So if your external magnetic field given is B0, your effective magnetic field is going to be lesser than the B0, and that effective magnetic field is given by B0 into 1 minus sigma, as sigma is your shielding constant. And this sigma is different for different nuclei of different electronic environment, and this is what actually making difference in the spectra to give you different Lama frequency of different protons. So now what is the effective, so if when we are discussing this, then your new L has become, it's nothing but gamma by 2 pi and B0 multiplied by 1 minus sigma. So now your different nuclei can have different Larmor frequency, but it is also true that this nu L is going to depend on your B0. So what you are measuring, the Larmor frequency measured by your instruments, your NMR instrument of a particular magnetic field should not be different what we are measuring here. Excuse me, I'm taking so sorry for that. Did anyone join? Yes, one person has joined. So we are talking about the chemical shifts here. So depending on the shielding constant, different atom or different nuclei is going to face different chemical shift. But this chemical shift, not exactly chemical shift right now, but the Larmor frequency cannot be different. As you can see, the nu L is proportional to B0, so it cannot be like that, that the Larmor frequency measured in our instrument is different from your instrument, right? So to do that, we need something, some reference, and that reference will lead us to a different scale other than this frequency, and that is the delta scale, or delta is also known as chemical shift for a particular nuclei, right? So the delta scale is for chemical shift. Okay. So this scale is a relative scale, and due to this relative scale, whatever, suppose, for example, we are taking ethanol. So ethanol has, as you remember, it is CH3 CH2OH. So from our discussion till now, what we have understood that there are, if we are discussing only about the proton NMRs, so there are three kind of proton nuclei are there because of their certain electronic levels. One is kind of methyl, one is alkyl, but it has effect from, so like these three protons will have a different environment, these two having a different environment, and this proton has a different environment, and due to that we are expecting three certain kinds of uh, Larmor frequency. Now what I was discussing, this three Larmor frequency cannot be different in different scales, so that a different instrument, so we need a relative scale, that's how this delta scale or chemical shift in ppm has been observed, and for this is given by, that delta is given by nu minus nu 0, where nu 0 is the uh, Larmor frequency for a reference, and this reference I'll talk it about soon. this multiplied by 10 to the power 6 ppm. As it is, as you can see that this is happening in uh, megahertz, so that's why this 10 to the power 6 factory was required. And this new, if we, let me go to the next page maybe. Okay, so we already know that this new is gamma b0 2 pi 1 minus sigma. So your delta is, so your new is dependent on b0, but as you can see when we took a reference for a particular case, so what we are going to have, this 1 minus sigma gamma b0 by 2 pi minus 1 minus sigma 0 gamma b0 2 pi, because these we are talking about the same nuclei, right, the proton, and divided by 1 minus sigma 0 gamma b0 by 2 pi. So from here we can obtain sigma 0 minus, and obviously into 10 to the power 6 ppm, sigma 0 by sigma 1 minus sigma 0 into 10 to the power 6. Okay. And this sigma 0, this shielding is actually very less, so one can ignore it here for now. 0 minus sigma into 10 to the power 6 parts per million. Okay. Now I'm going to show you some, it was already shown to you in the class by Professor Datta, that some characteristics chemical shifts for proton NMRs. Like if you see here that it is a delta scale and it is started from a 1 2 3 4, going from left to right, your delta value is increasing, and as you can see your different kind of functionality are there, right? In this region, from 1 to 2 there is CH or amine protons are NH2 primary amines, and then your CH2 or CH3 protons may be here. Then if you think about this 12 or 10 delta values there, if you see in the place of 10 there is aldehyde protons are there, in case of 12 there are acidic protons. Actually this portion is called the deshielded portion. So here actually your shielding constant is less for this, uh, and as shielding is less, you can see that they are much more affected by the effective nuclear charge. So these are the deshielded protons and these are the shielded protons. But same you will see with the 13C as well as, but I will not discuss much about this, but we will go to some numerical problems depending on based on these problems formulas. So these actually these numerical problems are taken from the book Atkins, Physical Chemistry by Atkins, on the problem page, and let us solve whatever formula we still went through or learned. Let us use those. But before starting, let me rewrite those formulas. So first one, we got that energy of a particular spin state would be given by minus gamma h cut mi b0, where gamma is your gyromagnetic ratio, h cut I will not reiterate, mi is your uh, spin value for a particular spin state. It is not a spin quantum number. Your spin quantum number is still I, which is half, or could be different for different integers, like but depending on the value of I, your mi would be, the values of mi could be from plus I to minus I. 2I plus one number of I, and B0 is your external magnetic field. So this is one formula, and again your gamma H you can write it in terms of your Bohr magnetron, the G value, nuclear G value, and nuclear magnetron, and obviously the next would be same. And the energy gap between two, that will come, but these are the main formulae what we are going to use. So let's start with the first numerical problem, which is 15.1a. What is the resonance frequency of a proton in magnetic field of 14.1 Tesla? So your B0 is given, that is 14.1 Tesla. What is the resonance frequency is going to be? And for a proton, so proton has two states, alpha and beta. So what is the energy gap between those? So that is your delta E, right? And that is your Larmor frequency is going to be there, right? And for that it is going to be in terms of, if I say this G factor and nuclear magneton, you are going to get it is as Gn mu n B0, right? Or in terms of gamma, you are going to get gamma H cross B0, because for proton there are two states, alpha which is plus half mi and beta which is minus half mi, right? So the gap between those are like this. Okay. Now B0 is given. So I'll give you the value of G factor. I already gave you, right? For I don't think I have given you, but right now let me give you the Gn value for the proton. That is something around 5.585. Okay, and the nuclear magneton value I have given, that is 5.01051 into 10 to the power minus 27 Joule Tesla inverse. So your nu L is going to be Gn mu n into B0 divided by your H, that is Planck constant. So G here is 5.585 into mu n is, we know, 5.01051 into 10 to the power minus 27 Joule Tesla inverse, and B0 is given 41.1 Tesla, and H you know, which is 6.626 into 10 to the power minus 34 Joule second. Now if you see the units, your Joule and Joule is going to cut, Tesla and Tesla inverse is going to cut, so it will be in second inverse or Hertz, in unit of Hertz. So let me calculate it and I will write it. So it will come as 5.585 into 5.051 into 10 to the power minus 27 multiplied by 14.1 divided by 6.626 by 10 to the power minus 34. So I am getting somewhere around 600 into 10 to the power 6. It is more than 600. So I don't want to write this many terms, but it is something around 600 megahertz. Okay, so this is how you can do. So I'll leave the problem 15.1b as the homework. Okay, so let me solve the next question. It is 15.22a. So where it is given 33s sulfur. So as you can see, it is a nuclear spin of 3 by 2, and we have already discussed, right? As you can see from 33s, the atomic mass is odd. So you expect that the nuclear spin is in half integer, and for obviously that is given 3 by 2. So and a nuclear G factor is also given, that is 0.4289. So we have to calculate the energy of the spin states in a magnetic field is also given. So first of all, so when there is no magnetic field, how many states are there? So the state will be 2 into 3 by 2 plus 1. So there are 2 into 3 by 2 plus 1, that is 4 nuclear spin state are there. So once the magnetic field is operating, then how it will look like? So I will draw it here. Pardon me for my bad drawing skills. It is not up to the scale, but still. So there are 4 nuclear states, spin state in presence of B0, right? What would be the states in terms of energy? If I say this is my energy scale, from going down to up is increasing, then if you remember your alpha or positive mi values having stability, right? So it is actually 3 by 2 plus 3 by 2 plus half, right, minus 1, right? How it will change? 3 by 2 minus 1 minus 2, so that is your minus half, and then minus 3 by 2. So these are your spin states. So what would be the energy associated with each? So I have written the formula here. As you can see, the G value is given for 33s. The G is how much? 0.4289. So we'll multiply for, so let us multiply for 1 and we'll get the idea. So what is the value of Gn into mu n into B0? B0 is also given, that is 7.5 Tesla. So mu n you already know, that nuclear magneton, and the value is 5.051 into 10 to the power. So I will not change that. 0.4289 and the magnetic field given is 7.5 Tesla. That is actually equals to 2.06 into 10 to the power minus 25 joules. Because the unit of Gn is none, it is Joule Tesla inverse, and it is Tesla. So Tesla number gone, Joule is remain. So that is there. Joule is obviously the energy of unit of energy is joules. Now we need to multiply with mi, right? So for this state plus 3 by 2, how much we are going to get into this, which will be 3 point, so the energy would be 3.085 into 10 to the power minus 25 joules, right? Minus sign would be there, obviously. Why? Because it is minus Gn, right? So obviously this would be plus 3.085 into 10 to the power minus 25 joules. As you can see, the energy values are very less, and that is why you want a radio frequency for a resonance to occur. So energy gap is very less. So let us calculate for half also. So it is something around 1 minus 1.03 into 10 to the power. I am taking the first two decibels up to 2 decimal points. Obviously it will be plus 1.03 into 10 to the power minus 25 joules. So is this what the question wants? Yes, calculate the energy of different states. That we have done. So I hope you will be able to do the same for 14N, right? 15.2b, where the question says the nuclear spin of half. Nuclear spin is 1, which is a full integer, right? Whole integer. Why? Because as you can see, it has a even atomic mass but a odd atomic number. So how many spin state it is going to have? If we can discuss, it is going to have 2 into 1 plus 1, that is 3 states, right? Plus 1, 0, minus 1. So okay, now let us go to question number 15.3a. I have on the next slide also. So okay, so calculate the frequency of separation of nuclear spin levels of a 13C, now 13 carbon nucleus in a magnetic field is given, magnetogyro ratio is there. So I'll written again here that the energy in terms of magnetogyro ratio I'll written right now. Okay, so the energy of a state Mi is going to be minus gamma h cut B0 Mi. I'll also write in terms of Gn and mu n. Okay, now for 13C. 13C also has half as I value, so it is plus half minus half. But gyrotic magnetic ratio is for, I'll write it here, 15.3a. So gyrotic magnetic ratio is given as 6.73 into 10 to the power 7 Tesla inverse second inverse. B0 is given, that is 14.4 Tesla. Frequency of separation for 13C, I can be, or you can say MIR plus half minus half, or I should write minus half plus half in terms of energy if you want to say. So that is your beta and this is alpha spin. So what would be the gap? So gap delta E is we have already discussed, which is gamma h cut B0. So here gamma B0 and h cut you already know, so frequency would be h nu L, alarm frequency will be gamma h cut B0. So nu L would be gamma B0 by 2 pi, which is gamma is given 6.73 into 10 to the power 7 Tesla inverse second inverse multiplied by 14.4 Tesla divided by 2 into 3.14. So your Tesla and Tesla will cut. So let us see how much will be the value. So it is 6.73 into 10 to the power 7 multiplied by 14.4 divided by 2 divided by 3.14. So that is coming around something around 154 megahertz More than that, I'm just taking up to the first three decimals. So if I can write it, it is something like 1.54 into 10 to the power 6 hertz. Hertz is nothing but second inverse. So that's why I have taken that. So did I make any mistake? Yes, I have made one mistake. Sorry for that. I'll just correct it here. It is 1.54 into 10 to the power 8. So that is why you're 154 megahertz. Anyway, so that is your Lamar frequency for this particular case. Same question is given for the 14N, but this case you have to remember you are now separating 14N. So your 14N has three states, right? Three states means plus 1, minus 1, plus 1, 0, minus 1. So you need to calculate the energy gap first, and based on that you need to calculate that. Okay, in that case your energy gap would be 2 into gamma h cross b0, or you can check whatever it is coming for the state with 0 I z a 0 mi. It is the energy will be 0 obviously, and it would be easy to calculate. Okay, anyway, so 15.3b is given for you as a homework. Now question number 15.4a: in which of these following system the energy separation is largest? A proton in 600 megahertz NMR spectrometer, or a deuterium in the same spectrophotometer? So energy gap again. So energy gap is given by this, or let's say this, right? So for a 600 megahertz NMR tube, NMR spectrophotometer means it has a specific B0 that is already defined. But what is not defined is that your mu n is obviously going to same for a proton and deuterium. So it is going to depend on the energy gap is going to depend on the G factors. Or even if you want to discuss that in terms of gyro-to-magnetic ratio, then your delta is going to be dependent on your gyro-to-magnetic ratio. Now for this question, let me write it down here, that the G factor of proton, one proton, or what is known as proton, we know is 5.8585, and the G factor for deuterium is 0.857, right? So obviously your delta E for proton, or the separation between a proton nucleus spin state of proton, is going to be higher than your delta E of 2H. Why? Because your Bohr magneton, or sorry, the G factor is different, and G factor is very less for deuterium. And why I have taken B0 as constant? Because B0, I told you when we are discussing that your new Larmor frequency is 600 megahertz, that actually defining your B0, that is constant for us. The NMR spectrophotometer is constant, same spectrophotometer they have mentioned. So that is what is going to happen for this. Now let us see what is the next question. The next question is a different one, that is 15.5a. Calculate the energy difference between the lowest and highest nucleus spin state of 14N. Okay, let's do it. So 15.5a, obviously what we have discussed till now, for nitrogen it will have three states, one with minus 1 spin, one with 0 mi, and another would be, so when I'm saying minus 1 spin, that is actually wrong. Your spin is 1, but mi has 3 different values, plus 1, 0, minus 1. So even if I am saying minus 1 spin, correct me, because I'm saying a wrong thing. Yeah. Now we already know what would be the energy for this state. It would be something like Gn minus mu n um, B0. This would be energy to 0 minus 1. That's minus 1 minus 1 will be plus 1. Here it is still minus 1 Gn mu n B0. So the energy gap between the lowest and the highest is actually 2 Gn mu n B0. B0 is given. Did we discuss the Gn for a 14N? I don't think we have done, but let me mention it here. Gn for a G value for a 14 nitrogen is 0.404. So the delta E is 2 into 0.404 multiplied by mu n, we know 5.051 into 10 to the power minus 27 joule Tesla inverse multiplied by the 15 Tesla magnetic unit. So Tesla magnetic cut. So let me calculate how much it will come. So 2 into 0.404 to 5.051 into 10 to the power minus 27 into 15. So that is coming around 6.12 into 10 to the power minus 26 joules. That is the energy difference between the spin states. So that's all for 15.5. What does 15.5b is asking? Calculate the magnetic field to satisfy the resonance condition for unshielded protons in 150 megahertz radio frequency field. So which is not exactly same, so we will do it, or else I would have told you to do it, but obviously we are dealing with the same formulas. So the formula would be, as you already know, nu L is gamma H, sorry, gamma B0 gamma B0 by 2 pi, right? So nu L is given, we need to find out what is BL is, and we also would have to know what is gamma value. Gamma for proton, I guess it is given in the previous question. So was it given? If not, then obviously we will go with whatever we know till now, right? So I am doing a back calculation. Gamma H cross by B0 will be 2 pi H cross. It is Gn mu n B0 by 2 pi H cross. Okay. Obviously it is Gn mu n B0 by H, and B0 B0 would be H nu L divided by Gn mu N. H we know 6.626 into 10 to the power minus 34 joule second. Larmor frequency is given 150 megahertz, which is 150 into 10 to the power 6. Okay, hertz is second inverse. Gn we know, that is why I converted from gyromagnetic ratio to this, that is 5.585 multiplied by mu n, nuclear magnetron, that value also we know, so that is 5.051 into 10 to the power minus 27 joule Tesla inverse, and this will lead to your joule cut, second inverse cut, and Tesla inverse will become Tesla as it is in the denominator. And let me calculate whatever value we are getting here. 6.626 into 10 to the power minus 34 into just into 10 to the power 6 divided by 5.585 divided by 5.051 divided by 10 to the power minus 27. It is coming something around 3.52 Tesla. I'm not sure if I have done a correct calculation, but this is the formula is what you will require to do this. Now next discuss the next problem, which is 15.6a. I hope 6a and 6b are the same, so we can discuss only one problem and give you another one to solve. 15.6a. Use table 15.2. Actually, this table was containing the GI values, which I have already taken, so don't worry. So the magnetic fields used to predict the magnetic field at which the proton, the deuterium, and 13C will come into resonance. Actually, I have the Gn value of the next series, so I'll do that. You may do the 6a yourself. So let me first write it, the G values. G value is 0.404 for 14N, 5.255 for 19F, for 13C, 31P it is 2.261. Okay. Now for I. So magnetic field is, I have given you the formula here, right? So at least we can get an idea that your B0 is going to be something constant divided by Gn, right? And obviously mu L is there. your h and mu n are constant, and I will write that value whatever it is coming. It is here. One point 31 into 10 to the power minus 7. Okay, so that is your joule second by joule Tesla, and the unit would be second by Tesla inverse. Okay. So here for 14N at 300 on the Larmor frequency at 300 megahertz, then and G we know, so then it is 300 into 10 to the power 6 second inverse into 1.31 into 10 to the power minus 7 seconds divided by, what is the G factor? G factor is 0.0404 for 14N, and your P0 would be something around 97 Tesla. So this much magnetic field you will require to split. Okay, now what about 750 megahertz? When your this is increasing, then your gap between the two states will again increase, right? So that would be something around 243. So this is for 300 megahertz, and this is for 750 megahertz. What about 19F? For 19F, we will just change the G value there. We already know what is the G value we have mentioned. That is 5.252255. For this, as the G value is higher, so for the 300 megahertz case, you are going to use only 7.48 Tesla. Magnetic field will be required for 750 megahertz. It is 18.7 Tesla. What about your 31P? The first case, so it's all about the calculation. These are fairly easy problems. For 750, you are actually going to need 2.261 is the G factor, 2.261. So you are up with 43.45 Tesla. And for 300, obviously you will need less because the separation will be less, 17.38. Okay. Now obviously you will be able to solve the 15.6a by yourself, but 15.7a on there is a different kind of question. Obviously we will try to do that. 15.7a. So the question says that calculate the relative population difference delta n by n for protons in the fields of different magnetic field. So what is delta n by n? So this is the difference, that is your number of beta spins minus the number of alpha spins. Or suppose I can also say number of alpha spins minus number of beta spins. Anywhere you can write divided by the total number of spins, right? If I take n alpha as common, then I get n beta by n alpha 1 plus n beta by n alpha. So n alpha will go, and delta n by n will be given as 1 minus n b by n alpha 1 plus n b by n alpha. And as you know, this population will be dependent on the Boltzmann constant or Boltzmann distribution, and that is given by the number of beta spin population of beta, obviously in the higher excited state, right? And alpha is down, so it is given by, if the population is dependent on the Boltzmann constant distribution, then it will be dependent upon, so it is proportional to exponential minus delta E by kBT, where kB is your Boltzmann constant, T is temperature, and the delta is the energy difference between beta and alpha, which we know, right? And this delta E is actually very smaller than, as we talked, these gaps are very small. So these gaps are very small in the thermal energy itself. So actually we can expand this minus delta E by kBT in terms of 1 minus delta E by kBT. This is that small. So we can ignore the higher order terms in the infinite series, and if we replace it here, this expression will become 1 minus 1 plus delta E by kBT divided by 1 plus 1 minus delta E by kBT, and that leads to delta E by kBT 2 minus delta E by kBT, right? And as delta E is very smaller than kBT, and so this delta E by kBT is obviously very going to be smaller than 2, so we can neglect it in the denominator, and what we are going to get as delta E by 2 kBT, right? So if we are, so in this question 15.7a we are talking about protons. So for protons, the delta E is Gn mu n B0, right? So and Gn being 5.585, mu n is 5.051 into 10 to the power minus 27 joule Tesla inverse, and B0 is varying here. And what is KB? KB is your Boltzmann constant, which is given by 1.38 into 10 to the power minus 23 joule Kelvin inverse. And as per the question, we are working at the temperature 25 degrees Celsius, which is 298 Kelvin. So we got almost everything, right? So we'll plug that thing here. So let us see how much we are going to get. Delta n by n is Gn is 5.585 multiplied by 5.051 into 10 to the power minus 27 joule Tesla inverse multiplied by B0, one of the B0, that is 0.3 Tesla, divided by 2 into 1.38 into 10 to the power minus 23 joule Kelvin inverse multiplied by 298 Kelvin. So let me calculate the value. Into 10 to the power minus 27 divided by 2 into 23. So it is coming something as at 0.3 Tesla. It is something as 1.03 into 10 to the power minus 6. It is very small number, right? The population difference delta n by n, obviously it is going to be very small. At B0 is 0.3 Tesla. Now obviously for 1.5 Tesla it is going to be higher, right? The gap, if you are uh, increasing the gap, then it will become at, suppose at 1.5 Tesla, it will be 5 times the before, right? So delta n by n at B equals to 1.5 Tesla is 5.14 into 10 to the power minus 6, and delta n by n at B equals to 10 Tesla is 10.3 6. Okay, no, I have written it wrong. I'm very sorry for that. Let me, for 10 Tesla it is 3.43 into 10 to the minus 5. Okay, so that's how you will be able to solve the next problems. 15.7b also. Now what is the question related to the 15.8a? So the question says the First generally available NMR spectrophotometers operated at a frequency of 60 MHz. Today it is not uncommon to use a spectrophotometer, that is spectrometer, that operates at 800 MHz. So what are the relative population difference of 13 C-spin states in these two spectrophotometers at 25 degrees centigrade? So there it is asking that at two different B0 what is going to be the thing, right? So let me do it here only. So delta n by n actually, if you see, is delta E by kBt. So it is dependent on delta E, and delta E is obviously dependent on B0, right? Or delta E is dependent on the Larmor frequency. So we get an early idea that the delta n by n for 800 megahertz would be, here it would be 800 megahertz, right? And the relative population difference at 60 megahertz would be divided by 60 megahertz. So it would be something as 80 by 6, which is 40 by 3, something around 13.33, right? Okay, so this is the relative population inversion. So if you increase the B value, so you are going to have a lot more difference in alpha and beta spin, and the more you have the difference, the more would be better for you to look. The resolution would be much more bigger, because the integration would be much more higher, right? Not the integration, but it would be, signal to noise ratio would be much good, as there are more difference in the number of alpha spin, and difference will be there between the alpha and beta spin. Okay, if the number is high, then the more transition would take place, right? And the more transition it would take place, the spectra, the signal to noise ratio would be good, right? That's why you are using a better spectrophotometer that operates 800 megahertz, not the earlier one which is operating on 60 megahertz. Okay, now let's see what are the next questions. So after this, actually 15.7a and 7b we have done. 15.8a also we have done. Good. Now what about 15.9a? The chemical shifts of CH3 protons in acetaldehyde ethanol is given. Delta is equal to 2.20 of that of CHO proton, so that is 9.80. So what is the difference in the local magnetic field between two regions of this? So to solve this question, so we have already discussed this, right? Your, what is the difference in the local magnetic field? So that is your delta B effective they want to know, right? But before delta B effective, what is B effective? So that is 1 minus sigma B0, right? That we have discussed. So delta B effective is of two different region of, suppose we are discussing the, so it would be 1 minus sealing constant of this CHO minus 1 minus sigma of this CH3 protons, right? Multiplied by B0. So this is nothing but B of effective of CHO minus B effective of CH3, right? So this is going to give me delta B effective as sigma CH3 minus sigma CHO B0. Now I will introduce one sigma 0 for reference. That is actually arbitrary, but see what I am trying to do it here. Sigma 0 minus sigma CHO minus, so I have taken this sigma 0, so I have to get rid of this, minus sigma 0 minus sigma CH3 B0. Okay, so what are these quantities exactly? So if you remember our delta scale, so the delta was is equal to nu minus nu 0 by nu 0 into 10 to the power 6 ppm, right? And what were nu? So we have discussed this, so I will just jump the steps to show you. This is nu 0 minus nu into 10 to the power 6 ppm. 1 minus delta 0 was there, but as delta 0 is very smaller than 1, that is why we are going to take it is nu 0 minus delta sigma 0 minus sigma. I'm very sorry, I'm talking if I am talking it about nu 0. Okay, this is 10 to the power 6 ppm, right? So we got something like this here, right? Nu 0 minus nu 0. So it is nu 0 minus nu 0 is actually delta of CHO into 10 to the power minus 6 ppm, right? Minus delta of CH3 into 10 to the power minus 6 ppm inverse multiplied by B0. Yeah, delta CHO is given, right? 9.8 minus 2.2 into 10 to the power minus 6 into B0, and these are ppm, so ppm minus are going to cut, right? So I have jumped that step. So 9.8 ppm and ppm inverse was there, so I am cutting that. So here the delta is just, they have written 2.20, but it is delta is equal to 2.20 ppm. Okay, just remember that. So this delta B effective for B0 of 1.5 Tesla is, so this is what, 9.8 minus 2.6, 7.6 into 10 to the power minus 6 into B0. So 1.5 would be, let me calculate quickly, it would be 7.6 into 10 to the power minus 6 multiplied by 1.5 Tesla, that is 7.6 into 10 to the power minus 6 into 1.5. That is actually very less. Obviously it is going to be very less, so the unit would be Tesla, and it is something around 0.00001114 Tesla. So this is the difference between them, and obviously delta B effective at B0 at 15 Tesla would be 10 times more than that. That is not much big, right? 1 0 would be gone. So 1 0 to 1 2 3 1 1 4 this something like this you're going to have. So the same theory you would be able to solve 15.9b, right? Great. So what about 15.10a? For question number 15.10a, sketch the appearance of 1H NMR spectrum of acetyldehyde using J equals to 2.90 Hz and spectrometer operating at this B value, but we'll refrain from doing this at this stage because and these chemical shift problems, because we'll discuss something about those coupling things and all, and the time is almost 7.45. We have 15 minutes around left, so I can discuss that coupling thing, right? But before doing that, let me get back to uh, the discussion we are having. Let me check if the recording is going on. Great. So we left it somewhere here, right? The characteristics chemical shift for the proton uh, where they resonate, and same for the carbon. So, and obviously this has been discussed in the class in details, that what is the effect of the ring currents, right? On aromatic system like a benzene ring, with the same ring current, for the same ring current you will see your B is operated on this Z axis along the Z. So some protons will be shielded and some proton will be deshielded due to the ring current. So that I'm not going to discuss in details, but here that for a ethanol, what we are saying that you expect a three different Larmor frequencies, and due to those three different Larmor frequencies you are going to have three different chemical shift values. But what you are seeing it here, that obviously that area under the curve will give you the integration number, right? The CH3 methyl one, which having a shift, some shift around here, so that will have an integration value of 3, and this CH2 should have an integration value of 2, this should have 3, and this should have 1, right? So these are three different protons, and their relative abundance will be the relative area under the curve. But what is interesting is that even after this many discussion up to chemical shift, you are seeing some fine spectra there. So what is the significance of these fine lines in the NMR spectra? So that is actually coming because of coupling between the spin. So already there is magnetic field which is uh, causing your spin state to have different energies, right? And then also your, suppose two different nuclei are there, so one nuclei is actually getting perturbed by uh, close nearby another nuclei is magnetic field. So it's not like um, another big magnet is coming. So this fine structure is actually due to a very small perturbation by another nuclei which is there in the close proximity. So that is why the spin coupling is going to happen, and you are going to see different multiplicity in your lines. Suppose for these methyl protons, actually they are going to split in three lines. You know the rule, right? 2ni plus 1. Here I is the spin for the proton, so I is half. So and n is the number of uh, proton in the nearest or nearby proximity, that is 2, right? And then on the next carbon there are 2, so 2 into 2 into half, that is 2 plus 1, so 2ni plus 1, that is 3. So that is why you are seeing a triplet in the case of this methyl one, and for stage 2 you are actually going to see three there are approximately 3 protons are there. Due to those 3 protons, actually you are going to see a splitting into 4, so that is known as quadrate. 3 2 into 3 into half plus 1, that is 4. Actually, why aren't you seeing something due to this OH? Because actually those are can be exchanged with the solvents, so they are not actually taking part in the coupling. Anyway, so we need to discuss that what is spin-spin coupling. So today what I'm going to do is that I'm not going to do so already Professor Datta has uh, done this thing in his lecture. I'm just trying to oh, oh, just like today we have solved some numerical problems so that you can have an idea. uh, but in these cases, like in the spin-spin coupling, there could be different thing, and I'm going to derive it, the whole thing. What Sir has done that he has shown up to a particular portion, and then he has asked us to do the rest of the thing at the home. So we'll try to do those things, a complete derivation of that coupling thing, whatever professor has done in the class on the day after tomorrow. But for now we will end with just the thing what coupling in a AX kind of system, and we'll not go into the quantum mechanical term, just we'll uh, see it axiomatically. So a coupling in AX kind of system. Why AX? So A and X are two different protons, suppose, or different nuclei, but their chemical shift is very different. So that's why this nomenclature is taken from the alphabet. A, X, they reside far apart from each other because their chemical environment is different, so as their chemical shift. So their chemical shift is very different of A nuclei and X. And it is given that your shielding constant for A is very less than shielding constant for X nuclei, and because of that your A nuclei is going to face much more effective nuclear charge, so the gap would be very high for this nuclei, means the gap between two spin states, and the gap between two spin states for X is going to be very small if they reside individually. But in this case it is a same system where AX two kind of protons are there, nuclei. So I will not say proton but nuclei, because this is true for all the other nuclei also. So it is a two spin system, two. So the two spin system, so the thing could be like your, there could be 4 cases, right? A have alpha spin, B have alpha spin, not B, right? It is AX system. So this is my mistake. X have alpha spin. What could be the other possibility? The other possibility is A has alpha spin, X has beta spin. Same, A have beta spin, X have alpha spin, and both of them have beta spin, then beta A, beta X. So what could be the relative energies of these states when in presence of magnetic field? Field, but no spin-spin coupling yet. Okay. So as you already know that alpha spins are going to be very in presence of magnetic field, the alpha with a plus half value, right? So they are going to have a very they are going to stabilized, and as both of them have alpha, so alpha A and alpha X are going to be pretty stabilized. So this would be the ground state. What about the same thing holds for beta A, beta X? That would be a highly unstable, or that would be similarly unstable as alpha X are stable. So they are the two extreme ends. What about the between one, alpha A, beta X, beta A, alpha X? Are they going to be degenerate, or are they going to have different energy? So that is, in this case, this condition is actually going to play a big role, that sigma A is less than sigma X. Okay. As I told you, sigma A is less than sigma X, the energy gap uh, between the uh, spin states of alpha and beta in case of A nuclei is going to be bigger than the case of uh, beta X, sorry, X. And due to that, your beta A and alpha A are going to reside at higher energy than alpha A and alpha X and beta X. So what I am trying to say, so there are two states. So we have already cleared that they are not going to be degenerate. Now which will be which state? So suppose I am writing this as alpha A, beta X, and this is as beta A, alpha X. So why I have done this? So if you see, when we go from this alpha A to alpha X to alpha A, beta X, we are changing the spin of X. So, and that is taking less energy than this transition when we are going from alpha A to beta A, because this energy gap is more as the shielding constant is less and the nuclei is facing much more effective nuclear charge, nuclear magnetic field, sorry. That is why the gap between beta A and alpha A is more. Okay, so that raised our this case that when there is no spin-spin coupling, this is the energy state, and the coupling is actually given by coupling energy is going to be dependent on something like h jax by h cut square, and then the spin vectors dot product of ia and ix. So I'm not going into deep of this today because we are going to anyway do the quantum mechanical treatment on the Tuesday. And so what that coupling is actually going to happen, so when the coupling is going to take place, so in presence of coupling, so I'm giving you the result, and we will discuss how that we got that to the next day. So actually what you are going to see that this state is actually going to destabilized by some amount, that is h j by 4. Alpha x and beta x are actually going to stabilize by the same factor. So this is your alpha a beta x, this is your alpha a beta alpha a alpha x by the same factor, that is aj by 4. Similarly, this state is also going to be stabilized by the same factor but your this state is going to destabilize beta A beta X. Okay, that is going to destabilize by the same factor. Sorry, here I have written it wrong. And this will be your new, so this is your energy scale, and this is going to be your new energy state in presence of coupling. So earlier you are expecting, so this transition would give you new A, this would give you new X. Similarly, this transition between 4th and 2 would have give you new A, and 3rd and 4th would have been given you new X. So you are expecting two spectra, new X and new A, but due to this stabilization and destabilization due to coupling, what you are going to see is actually instead of these two, you are going to see something around here and here. So we'll discuss it tomorrow. What are these? But the gap between this and this would be Z by 2, Z by 2, Z by 2, Z by 2, and the overall gap is obviously Z, right? So that is your coupling constant. So actually instead of 2, you are going to see this splitting due to the coupling between the spin state of A and X. So that is what we are going to discuss in the next class in quantum mechanically, what we are going to get. And before that, so with that we will stop today's session here. I hope the session was informative, and hopefully we have solved a few numerical problems which will help you to solve the assignment problems and score well in the final examination. And with that, today we will stop. I think we have one student with us, Naveen Babu Borugadda. Hi, Mr. Naveen. So how was the session? Did you have any question, or we can close the session? So that means I hope you don't have any you don't close. Okay, okay. So I got your message. Okay. So with that, today we'll stop it, and thank you for joining. Um, we will meet on the day after tomorrow, Tuesday, on the final session. Thank you for joining.